Welcome back to my channel. Today we're going to talk about simplifying radicals. So how to simplify radicals. And look at a bunch of cases here. Radical, we need to know that a radical is that root symbol, square root, cube root. It's that little sort of boxy shape that's called a radical. And the thing with simplifying is it can involve a lot of things. We could be talking about adding radicals, subtracting, multiplying them, dividing them. Let's look at some radical cases that probably you already know. If I said the square root of 25, you're probably going to tell me the answer is 5, and you'd be correct. And the square root of, I don't know, let's say 121 equals 11. All right, and this sort of gets to the idea that some square roots don't require any work at all. It's good when you're doing simplifying to know what your perfect squares are. So 1, 4, 9, 16, 25, 36, let's even keep going, 49, 64, 81, 100, 121, and 144. So it's important, I think, to know your first 12 perfect squares. So let's take a look here. If I say, what's the square root of 32? Well, the issue with 32 is it isn't a perfect square. It's not in that list. But I can use that list to figure out if there's another perfect square that's embedded in the 32. And I know that 16 goes into 32. So what I can do is write that as 16 times 2. Now, why is that helpful? Well, there's a little known rule in math which says you can pull these apart. If that's a multiply between the two numbers under the radical, I can write that as a square root of 16 times the square root of 2. And we know what the square root of 16 is. It's 4. So that's going to be equal to 4. Now the 2 gets stuck inside the radical. Because it's not a perfect square, I'd need a calculator to get that decimal approximation, so I leave it just like that. Let's try another one, but this time let's put a coefficient. Maybe -2 square root 50. Okay, now 50 is not a perfect square, but look, 25 is, and 25 goes into it. So what I could do is just leave the -2. The idea of simplifying is trying to get as much number out of the radical and in front of it as possible. So the work here is going to be on the 50. -2 sticks. I know that 50 is 25 times 2, and I know that the square root of 25 is 5, so that's -2 times 5. Notice I'm skipping a step here. You can start abbreviating your work. The 2 gets stuck inside, and that's going to be -2. I multiply these numbers. -2 times 5 is -10, -10 root 2. Okay? All right, so some questions won't be square root land, they'll be cube root land. So just like we want to know our perfect squares, we want to know our perfect cubes. I usually say to students, know your first 5. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and 5 cubed is 125. Okay? So know those first 5 because they come up an awful lot. So if you were asked to say, find the cube root of, I'll just say 64, that one doesn't require too much work, and usually your tests will be calculator permitted. So in this case, you could just type in the cube root of 64 and you would find the answer is 4. But what happens if we're asked to take the cube root of, oh, I don't know, let's say 54? Well, now the problem is 54, well, it fits between 27 and 64, so it's not a perfect cube. But we could break it down because we know that within 54, with a little bit of thinking, 27 does go into 54. So 54 includes a perfect cube. So what I'm going to do is rewrite 54 as the product of 27 times 2. Why? Because I know that the cube root of 27 is a number that I can figure out, and the goal is to get as much number out of the radical as possible. So this is going to turn out to be the cube root of 27 times the cube root of 2. Do you see? And then the cube root of 27 is 3, which is 3. I replace that. So notice the whole thing goes away and becomes 3, and then times the cube root of 2. And if I put this into my calculator, and I put this into my calculator, I would get the same answer. They would be equivalent decimal approximations. So sometimes simplify means add radicals or subtracting radicals. So if I had 3 root 7 and I was going to add that to 5 root 7 and then subtract root 7, then I can combine those, simplify them. One term is more simple than 3 by simply adding the coefficients. Do you see there's a coefficient there? It's 1, minus 1. So 3 plus 5 is 8. 8 minus 1 is 7. So the answer is 7 root 7. So there's an example of adding them. Sometimes they don't appear to be combinable. So for instance, you might have the square root of 32 minus 5 root 2. And they don't look like you can put them together. It doesn't look like apples with apples. It looks like apples and oranges. But 32 does have a perfect square built into it. Do you see? So what I can do is simplify this first. So 16 is the number I'm after. 16 times 2 is 32 minus 5 root 2. And the square root of 16 is 4. So that's going to be 4. The 2 gets stuck on the inside, root 2, minus 5 root 2. So root 32 is an unsuspecting like radical with 5 root 2. And now that the radicals are the same and the indices are the same, you can simply add, subtract the coefficients. So 5 minus 4 is negative 1 root 2, or you can simply write it as negative root 2. And sometimes simplifying can mean multiplying two radicals or dividing radicals. So let's take a look at these. So multiplying radicals are kind of easy. You simply have to multiply the coefficient parts. A good old guess would probably get you the right answer. So negative 3 times 5 is negative 15. And then numbers under the radicals can also be combined in a multiplying way. So 6 times 2 is 12. But you have to make sure that you simplify the inside radical. In other words, if there's more number to come out, you got to take it out. Well, what perfect square goes into 12? Well, 4 goes into it, right? So I can write that as negative 15 square root 4 times 3, and the square root of 4 is 2. So that's going to be equal to negative 15 times 2. The square root of 4 is 2. The square root of 3 is the square root of 3. Right? The square root of 3 is irrational. If you wanted to get another number, you'd have to be taking a decimal approximation using your calculator. And then you times these. Everything's glued together by times. Negative 15 times 2 is negative 30. Negative 30 root 3. All right. Now, this is a divide question. So when you do a divide, check to see if the coefficients divide into each other. Do you see negative 5 goes into 15? And also the numbers under the radical, those are called the radicands, who cares? If this little denominator down here, the little baby radical, goes into the other baby up here, then this becomes easy. Watch what happens. I just divide the 15 by the negative 5, which gives me negative 3. And then the 2 goes into the 18. That can be thought of as 18 over 2. Well, 18 over 2 is 9. And what's the square root of 9? It's 3. So that turns out to be negative 3 times 3, or negative 9. Now sometimes the divide looks like this. It's a number over a number. Any number divided by a number is a fraction. And a fraction is a divide. The issue here is having a radical downstairs. We can't have that. We can't have an irrational denominator. So what we do is multiply by 1 by multiplying both the top and the bottom by root 3. If that had been root 2, we would have chosen root 2 over root 2. And notice that root 3 over root 3 is just 1. It doesn't change the number. It makes it look different, and that's it. The magic here is by multiplying now. So multiplying fractions, 1 times root 3 is root 3. And root 3 times root 3 is root 9. And root 9 is 3. So this actually is a better way to write the answer than the original way it was written. Do you notice now the denominator is rational? 3 is a rational number, and root 3 was irrational. So this version here is considered best. Now sometimes the division has a binomial denominator. So you can see now it's 1 plus root 2. Now if there was no 1 plus, it was just root 2, we would do what we just previously did. We would multiply by root 2 over root 2. We can't do that here. It won't work. You can try, but it won't work. So we use this other trick. Math is about tricks, right? If it works, then all's well that ends well. What we do is we take the conjugate of this denominator. It's a really easy thing. It's simply the same numbers, 1 and root 2, but you change the middle sign. So positive goes negative. And if this had been negative, that would go positive. Brackets start with the letter B, so do binomials. So put brackets around your binomials. Here, 1 minus root 2. Again, I'm just using this principle of multiplying by 1. It doesn't change the value of it. It just changes the form, or what it looks like, so that we don't have an irrational denominator. Once I have this, I simply expand through. So negative 3 times this is, I can think of fishing it through, or however you think of it. Negative 3 times 1 is negative 3. And negative 3 times negative root 2 is positive 3 root 2. In the denominator, first, outside, inside, last. So we've talked about FOIL on this channel before. 1 times 1 is 1. 1 times negative root 2 is negative root 2. Root 2 times 1 is positive root 2. And positive root 2 times negative root 2 is negative 2, right? When you take a radical and multiply it by an identical radical, then the answer is simply just the number under the radical. For the brilliance here, it's the O and the I. The O and the I in FOIL cancel. That's why we use the conjugate. That's why it works. The upstairs doesn't change. So the numerator is still negative 3 plus 3 root 2. And then I get a 1 minus 2, which is negative 1. We don't like to leave denominators as negative. It's not the worst thing to do, but we don't like that. So you can simply multiply everything by negative 1 upstairs and down. So multiply by negative 1, multiply by negative 1. The negative 1 gets brought through. The denominator is now just 1. Negative 1 times negative 3 is 3. Negative 1 times positive 3 root 2 is negative 3 root 2. Or just simply 3 minus 3 root 2. All right, so those are the big ticket issues when it comes to simplifying radicals. I've got lots more videos with more details and a little more challenging examples on this very YouTube page. So look at my other videos if they help. And don't forget to slap a like on this video if it's helpful for you. Share it with someone who might benefit, and don't forget to subscribe.